In the previous class, what did we do? We did the Reol's law, we also did certain questions, and we were doing liquid solutions or liquid mixtures in which we had considered miscible liquids, right? So miscible liquids, as you all know, they are homogeneous mixtures and thus they are known as solutions. According to the miscible liquids, we discussed the Reol's law and we classified the solutions into ideal and non-ideal solutions. Now today we are going to carry forward what we had done in our previous class. What we are going to do today is, what do we understand by the term distillation and fractional distillation? You all know that what is distillation. When we are we are separating two different components of a mixture because they have different boiling points through the Lebesgue condenser, which you have done in your junior classes in class 11. So that condenser helps us to separate both the components of a mixture. Now if there is very little difference between the boiling point of the two liquids, then simple distillation that does not work. So we have to take into consideration a little sophisticated kind of distillation which is known as fractional distillation. Now today we are going to club the topics. We are going to take fractional distillation and we are going to consider the ideal and non-ideal solutions. Let's first of all do the ideal solutions. Now it is very easy for us to study the fractional distillation by way of graphical representation, right? So I have already drawn the graphs for three, that is ideal solutions, positive deviation and negative deviation. It is said that we are able to separate the two liquids or the two components of any miscible solution or miscible mixture only if there is a difference in composition between the liquid phase and the vapor phase, right? Which means that the composition of the liquid phase is different and the composition of the vapor phase is different. What do we understand by composition over here? It is the mole fraction which we had already done in the Reol's law, and when we clubbed both the Reol's law and the Dalton's law. So Dalton's law and Reol's law when clubbed give us the mole fraction in the vapor phase. So we are going to consider in these graphs the composition in the vapor phase and the composition and in the liquid phase. So let's go on to the first type of solution over here, which is known as the ideal solution, right? So first understand what the graph is all about so that it becomes easier for you to understand rest of the graphs. Over here in ideal solutions, when we are talking of the upper line over here that shows the line for the vapor phase and the lower one that is showing us the line for the graph for the liquid phase, right? On this axis we are taking the boiling point or the temperature, and on this axis we are taking the composition. So over here A is equal to 100% and over here B is equal to 100%. So A is decreasing, the composition of A is decreasing as we are moving from left to right, and the composition of B is increasing as we are moving from left to right. Okay, so now what is happening over here is that when we are talking of this kind of solution, we take a solution of composition X. Right? We are taking a solution of composition X, and for composition X, when we start heating, we are saying that at this particular point, the temperature at which the composition will start boiling, that is Tx. Right? So at Tx, we say that the temperature it starts boiling, and the composition of the vapor phase at Tx, you can see over here, that comes to x1. Right? Similarly, we are taking composition Y at Ty, okay, and the composition at Ty for the vapor phase that is going to be equal to Y1. So we have different compositions over here. Let's understand what is happening. We are saying that when a solution of composition X is heated, right? When a solution of composition X is heated, the temperature keeps on increasing and it reaches a temperature Tx when the mixture starts boiling. At Tx, the composition of the vapor phase is X1, right? Now when the composition of the vapor phase, that is X1, we say that according to the graph, the vapor phase is richer in B because it is closer to B, right? So the vapors of the mixture will be richer in B and the distillate, that is the liquid which is left behind, that is going to be richer in A because it is closer to A. Okay, on further boiling, what is going to happen? When we start boiling it further, we see that a temperature Ty is reached. Okay, at this particular temperature Ty, the composition of the liquid, that is Y, right, which is again closer to A. So the liquid is again closer to A and the composition in the vapor phase is closer to B. So the liquid is going to be rich in A and the vapor is going to be rich in B. Slowly and gradually, as we keep heating, the liquid will keep on becoming richer in A. Now if we further heat it, we will see that the liquid will become richer in A and the vapor that will keep on becoming richer in B, right? So at one particular temperature, a temperature will come when we can distill A in the form of the liquid and the vapor will only contain composition of B. Vapor will only contain B. Then by cooling the vapor in fragments, we cool it, then we separate out B, then we again cool it and we separate out B. In this manner, for ideal solutions, the composition of the vapor and the liquid phase is different, right? The composition of the vapor phase and liquid phase is different. So for such solutions, by constantly boiling and by fractional distillation, we can separate A and we can separate B, right? So fractional distillation for such solutions can give us ultimately pure A and pure B. Have you understood? Then let's consider the second type of graph which we have put over here, which is the positive deviation. Now in positive deviation, we have already studied according to Réal's law that the total pressure that is going to be greater than the sum total of PA and PB. This we have done. So I am just going to put it over here. Total pressure is greater than PA and PB, and for ideal solution, total pressure that is equal to PA plus PB. Okay, and over here we are saying in negative deviation the total pressure is less than PA and PB. Now when in the second graph, which we can see over here, we are looking at a point C, right? At point C, the composition of the vapor phase and the composition of the liquid phase is same. Okay, so at this particular point, the temperature of the solution that becomes equal to T. So at T, we cannot separate completely A and B, and at point C, the temperature becomes constant. Okay, so this is known as what? Such solutions, they are said to be known as constant boiling mixtures. Constant boiling mixtures, or another name which can be given Now as in this graph, a minima is observed, right? If a minima is observed, this means that this is minimum boiling azeotropes, right? You can see that the boiling point of the pure component A is here, the boiling point of the pure component B is here, but the boiling point of the mixture, that is lesser than A and that is lesser than B. So positive deviation, when we are talking of these positive deviations, they are going to result in minimum boiling azeotropes. So this is a graph for minimum boiling azeotropes. Let's understand the graph over here. When we are talking of the graph over here, we say that at point C, the temperature T is reached, right? And at temperature T, there is going to be no change in composition. The composition is going to be fixed. Okay. Now let's understand what's happening over here. Let's say we are taking a mixture of composition X, right? We are taking a mixture of composition X, and when we start heating this, the composition of the vapor phase, that is going to be what? X1. Okay, the composition of the vapor phase is going to be X1. So at this particular temperature, the distillate, that is the liquid or the residue, that is more towards A, and the vapor phase X1 is more towards B. Same over here we are taking, this is A is equal to 100%, and over here B is equal to 100%, right? So we are saying that if a composition of X is taken and we start heating, so X is more towards A and X is more towards A. That means the composition of A over here, that is going to be greater, right? In a similar manner, on further heating, what we find over here is that the composition of Y is more towards B, right? So when we keep heating the mixture, a point will come, which is point C, in which both the vapor and the liquid phase that coexist. So at this particular point, if we want to separate out A and B, it cannot happen. At point C, for such mixtures, we can never, you can say, distillate 100% of either of the components in these kind of solutions. So these are known as what? They are known as minimum boiling azeotropes. Examples we will talk of later. Let's understand the negative deviation. And negative deviation, what can you see over here? There is a maxima over here. Okay, if the boiling point of A is this much, over here at this point A is going to be 100%, and at this point B is going to be 100%, right? So when we start heating, we have X and X1 is lying more towards A. In a similar manner, Y1 is lying more towards B. But then on further heating, we get a point C where both the vapor and the liquid phase, they are going to coexist. The vapor phase is this and the liquid phase is this, right? So at point C, the distillate which we have is neither pure A nor pure B. It is a mixture of both. So over here also we can point out that at this particular temperature we cannot distill A and B purely, and because we are having a maxima over here, these type of solutions, they are known as what? They are known as maximum boiling azeotropes. Okay, so we are going to take examples of both now. Let's first take example minimum boiling azeotropes. An example which we can take over here is that of water plus ethanol. Water plus ethanol. Now, percentage composition of the azeotrope, that is, we are talking of the percentage composition at C. At C, we can only distill 95.97% of alcohol. Right? And the temperature which is coming over here at point C, that is 78.15 degrees Celsius, which is lesser than both water and alcohol. Is it clear? Second example we can take is pyridine and water. Pyridine plus water. In this, again at point C, we cannot completely distill both, but the composition is 57% pyridine. And the constant boiling temperature over here, that is 92.60. 92.60 degrees Celsius. Right? In a similar manner, we can take certain examples of maximum boiling azeotropes. Maximum boiling azeotropes. For maximum boiling azeotropes, in the graph you can see that a maximum is observed. An example which we can take over here is that of HCl plus water. At point C, we can only distill 79.8% of water. And the temperature, the constant boiling temperature over here, that is going to be higher than both HCl and water, so it comes to 108 degrees Celsius. Okay, then another example we can take over here is HNO3 plus water, right? Here at C we can distill 68% of water. Okay, and the temperature over here is going to be higher than HNO3 and water both. It is 125.5 degrees. 125.5 degrees centigrade. So these are what we understand by azeotropic mixtures or constant boiling mixtures. Today we are going to discuss the second type of solutions. Now we have discussed number one, gas and liquid. The second we discussed liquid and liquid. So the third solutions which we are going to discuss today is solids in liquids. So we have solutions of solid and liquid. This is a very common kind of solutions which we keep doing. Like we have in our day-to-day life, we have sugar in water, we have salt in water. So these are certain homogeneous mixtures which are taken as solutions in our daily lives. Now when we are talking of solutions of solid and liquids, we come across three different words. Like we know what we come across unsaturated solutions. Now what is unsaturated solutions? Unsaturated solution means that when we are able to dissolve more solute in a particular amount of solvent, that is known as unsaturated solution. Right? Now if we will keep adding the solute, a point will come when no more of the solute that dissolves in water. The solute that refuses to dissolve in water, such kind of solutions, they are known as what? They are known as saturated solutions. Right? So saturated solutions, in saturated solutions, when we are trying to put more solute, no more of the solute dissolves. That is what saturated solution is. If we increase the temperature, the solute, it starts dissolving. Right? But at higher temperature, when no more of the solute dissolves, then that is known as a supersaturated solution. Supersaturated solutions, when cooled down, they generally recrystallize to have certain solute settle down at the bottom. Okay, so this is what saturated and unsaturated, so saturated and supersaturated solution means. Now, when we are talking of the solutions of or the dissolution of solid in a liquid, we say that there are two processes taking place. The first one, that is known as dissolution. Now, dissolution is when particles of a solute leaving the solid and dissolving in the solvent. The particles of the solute, they leave the solid and they start dissolving in the solvent. That is known as dissolution. And the other process which is taking place, that is known as recrystallization. What do we understand by recrystallization? The solute particles, they have started coming together again, leaving the solvent particles. So that is recrystallization. Now at equilibrium, we are saying the solute in the solid form gets dissolved to form solute in the dissolved form. So the forward reaction, that is known as dissolution, and the reverse reaction, that is going to be known as crystallization. Both, that is, if we are talking of this equation, the solute in the solid state and the solute in the dissolved state, they are both in dynamic equilibrium with each other, which means this keeps changing into that, and that keeps changing into this. And at equilibrium, both the processes, they are occurring with same pace. So that is the reason we cannot see. We know what equilibrium is. When forward reaction becomes equal to backward reaction, that is what is equilibrium. Okay. So at equilibrium, we can see both. Now, what are the factors which are going to influence the dissolution process? What are the factors which are going to influence the dissolution process? The first one, that is nature of the solute. Nature of the solute. Now we know that in chemistry there is a principle like dissolves like. Okay, like dissolves like का मतलब कि if we are taking a polar or an ionic solute, that will dissolve in an ionic or polar solvent, and if we are taking a non-polar solute, that is going to dissolve in a non-polar or organic solvent. Okay, so basically we have water, we generally take as a universal solvent, or water is taken as an ionic solvent. So in water, all the polar and the ionic solutes, they are going to dissolve. But there are other things, like we are talking of solubility. Solubility means what? Solubility means the specific amount of solute dissolving in 100 grams of a solvent. That is what solubility is, right? So when we are talking of solubility of any particular solute, the solubility of a solute depends upon two things. First, it will depend upon lattice energy. What do we understand by lattice energy? It is the energy with which the ions they are bound in a crystal. Okay, so if the lattice energy is going to be higher, if the lattice energy it is going to be higher, the ions will be more strongly bound. Okay, so all the solutes having high lattice energy, they are not very soluble in water. For example, which we can take over here is of barium sulfate. So lattice energy is the energy between, or you can say it is the interaction between the solute and the solute particles. In a similar manner, there is another energy which we take into consideration over here, that is due to the forces of attraction between the solute and the solvent. Right? Forces of attraction between the solute and the solvent. That is, when the solute it is getting mixed with the solvent, a certain amount of energy is going to be released. So this energy that is known as hydration energy. Okay, this energy that is known as hydration energy. Now, if the interaction between the solute and the solvent particles is going to be more, obviously dissolution is going to be more or solubility is going to be more. So all those which have a high value of hydration energy, they are going to be more soluble. So we sum up in 2 points. If the lattice energy is less, the solubility is more. If the hydration energy is more, the solubility is going to be more. So the dissolution is a combined effect of both lattice energy and hydration energy. Right? And the resultant energy should always be negative for the dissolution process to take place. This you have studied in S block elements in class 11. Right? So I am just summing it up that if the lattice energy is more, dissolution is less, and if the hydration energy is more, dissolution is going to be more. Okay? Then second, it depends upon what? Nature of solvent. As we have already studied that polar solutes or ionic solutes are going to dissolve in polar solvents, right? But over here we will like to mention another thing, that the ionic solutes, they are going to be soluble in those solvents which have high dielectric constant, right? For example, we are talking of water. Water, it has a dielectric constant of 80. And if we are taking the dielectric constant of ethyl alcohol, it is only 33.5. Okay, so as the dielectric constant of water is more, therefore ionic solutes, they dissolve better in water than in C2H5OH. And the dielectric constant of benzene, it is very, very low. It is only 2.3. So benzene does not dissolve ionic solutes at all. Okay. Then the third factor which we add over here, that is pressure. We know that the solids, they are incompressible. We cannot deform the solids by applying pressure. Therefore, pressure does not have much effect of the dissolution of solids in liquids. The next factor which we are going to do is temperature, which is very, very important. Now, to study the effect of temperature, we are coming up with a graph over here on the board. Okay, so you can study the various solutes, the effect of temperature on the solubility of various solutes in this particular graph. This is also known as the solubility graphs of various solids. Okay, so mixing the solute and the solvent, energy may be released, energy may be absorbed. So for both the cases, the effect of temperature, that is going to be different. Okay, for example, if we are dissolving potassium iodide in water, we see that on mixing, on continuously stirring the mixture, we see that the tumbler in which we are doing the dissolution process, that becomes hot or warm. It means that energy is being, it becomes cooler, which means that energy is being absorbed. So certain processes, they are known as what? They are known as endothermic process. Okay, so for endothermic process, where the energy that is absorbed or heat is absorbed, the solubility increases. Solubility increases with increase in temperature. Right? As you can see in the graph, there is a very sharp increase in solubility for AgNO3 and potassium iodide. Right? The top two lines which we can see over here, AgNO3 and potassium iodide, there is a steep increase in solubility by increase in temperature. Then below you can see for NaCl also there is a slight increase, very slight increase in solubility with increase in temperature. So for all endothermic processes, the solubility increases with increase in temperature. Then we have the second one. Exothermic. Right? For exothermic processes, when we are mixing the solute and the solvent, here the tumbler that is going to become warm. So which means that energy that is being released. For such processes, solubility decreases with increase in temperature. Solubility that is going to decrease with increase in temperature. Right? Then we come to certain salts which are hydrated. Hydrated salts are those which have water of crystallization. As for example, sodium sulfate decahydrate, which is known as Glauber's salt. For such cases, as you can see in the graph, that initially the solubility increases with increase in temperature, which means that initially the process is endothermic till the entire water of crystallization is lost. Okay, so when once these 10 water of crystallization are lost, the solubility takes a dip. The solubility starts decreasing with increase in temperature as the process becomes exothermic. Now at one particular temperature from where the dip starts, the temperature for Na2SO4 10H2O, that is 32.3 degrees. This is known as the transition temperature. Clear? This is known as the transition temperature. Now for salts, like as you can see, salts like calcium chloride, hexahydrate, salts like calcium chloride, hexahydrate, there are, in the graph there are two maxima. Okay, now in the first step, it is only losing 2 molecules of water to form calcium chloride dot 4H2O. reaches this point, then the solubility decreases a little and then it starts increasing again till it loses all its water molecules and hence it starts